All right, hi folks, this is Larry Maslino. I'm recording a video to help you get started on the Module 7, Chapter 10 homework here in my lab. And Chapter 10 and Chapter 11 really are dealing with what are called confidence intervals. And quick background, a confidence interval is a way to estimate a population measurement, a population parameter. Let's say we have an unknown population mean. We use mu to indicate the population mean. Well, I don't have any way to know what the population mean is, but I can take a sample. So I take a sample and find the sample mean. And the sample mean is X bar. What we're going to end up doing for a confidence interval is finding what's called a margin of error. A margin of error is giving you an idea of how far off your estimate, X bar, is away from the true population mean that's unknown. And then what we do to form this confidence interval is we take X bar minus this margin of error E. We call this the lower bound. And then we take X bar plus E. We call this the upper bound. And these two numbers form the confidence interval. Sometimes we put these in parentheses like this. We can do the same thing with proportions. So there's an unknown population proportion. We call it P. Let's say I want to know the percentage of smokers for all adults in the United States. Let me erase some of this to give a little more room. So let's do an example for an unknown population proportion. Okay, I want to know, let's say, the percentage of smokers in the United States. Well, there's no way I can go out and collect data from every adult in the United States, right? That's impossible. So what I'm going to do is I'm going to take a sample. I'm going to take a sample of, let's say, 200 people. And from those 200 people, I find out that 24% of them are smokers. 0.24 is the proportion. Now we use P hat to indicate the sample proportion. Let's give an example here. Let's say the margin of error turns out to be 0.05. All right, I'm going to set up the confidence interval now. The confidence interval is going to be taking P hat minus E. That's going to be the lower bound. And then P hat plus E, that's going to be the lower bound. For our example, this is going to be 0.24 minus 0.05 for the lower bound and 0.24 plus 0.05 for the upper bound. So that's going to be 0.19 and 0.29. Sometimes you put the confidence interval in parentheses like that. So here's my statement. I am 95% confident. I'm using 95% because that's a typical confidence level we use. I'm 95% confident that the true proportion of smokers for all adults in the United States, remember that's P, is between 19% and 29%. So what this confidence interval does is it allows me to take sample data and use that sample data to make a statement about the population proportion. So the final statement you always make with a confidence interval is a statement about the population proportion. So I'm saying the true proportion of all smokers, that's the population proportion. All right, so let's do a few examples here in Chapter 10. Let's do this first one. It says an investment website can tell which devices people are using to access the site. The site managers are wondering, should they enhance for trading via smartphones? So they want to estimate the proportion of users who access the site using smartphones. So they're going to take a random sample of 100 investors. So the sample size here is 100. And the proportion, the true proportion of smartphone users is 34%. Well, that's the population proportion. So I'm going to use P equals 0.34. Usually we don't know the population proportion, but in this example, they're saying to us, suppose the proportion of smartphone users is 34%. Well, what if you started taking samples of size 100? And for each one of these samples, you calculated p hat. That's the sample proportion. So I'm going to calculate all of these different p hats for different samples of 100 people each. What would you expect the shape of the sampling distributions of these p hats to look like? Well, there's something called the central limit theorem that tells us that if the sample size is large enough, these p hats are going to follow a normal distribution. So if I was to plot the p hats, we would end up seeing a normal curve. And what we would expect is the center of this curve would be at 0.34, because that's the population proportion. What if the sample size were increased to 400? Would that change any of these answers? No. If the sample size was larger, the shape and symmetry would still be the same. There would the distribution of these p hats would still follow a normal distribution. All right, let's do an example. Oh, by the way, we didn't do part B. It says, what would be the mean of the sampling distribution? Well, the mean of the sampling distribution is the same as the population proportion. In this case, it's 0.3. All right, let's do another example here. So this one says the proportion of adult women in a certain geographic region is 49%. What if you conduct a survey where you call up 100 people at random? What proportion of women would you expect to see in the sample of 100? Well, if the population proportion is 0.49, and I take a sample of 100 people, I would expect the sample proportion to be the same, 0.49. How many women would you expect to find in the sample? Well, if there's 100 people in the sample and 49% of them are women, that tells me there would be 49 women expected in the sample. Now, I may not see exactly 49 women, but I would expect to see approximately 49 women. All right, let's do another example here. So it says here, a market researcher wants to know the proportion of customers who own cars. They took a survey of 400 customers, so that's the sample size. And in the sample, 76% own cars. So P hat is 76%. I'll write it as 0.76. Let's go to part A. It says, what is the estimated standard deviation of the sampling distribution of the proportion? So what that means is if you took repeated samples of size 400 and you calculated a sample proportion for many samples, what would the standard deviation of these p hats be? That's what they're asking us here. Well, there's a formula for this. The standard deviation, let's do part A here. The standard deviation for the sampling distribution is the square root of P times Q over N. Now this letter Q is really just 1 minus P. So in our example, this is going to be the square root of 0.76 times 1 minus 0.76 all over the sample size, which is 400. And if you work this out on your calculator, you should end up with the answer 0.021. Let's go to part B. Part B is the same question, But for part B, they're changing the sample size to 100. So now n equals 100. Well, it's going to be the same kind of calculation. It's going to be 0.76, 1 minus 0.76, but now the sample size is 100. So I'm going to put 100 down here in the denominator. If you work this out on your calculator, you should get 0.0427. Of course, be careful with the rounding instructions. This problem says round to 4 decimal places. So be sure you're rounding to 4 decimal places. All right, let's do a couple more. Let's do this one. It says you take a sample of 200 people who've already received the vaccine. I'm sorry, you take a sample of 200 and you want to know how many received the vaccine. You find 46% did. So you're coming up now with a 95% confidence interval of 0.39 to 0.53. So let's write this down. The sample size here was 200. The sample proportion, we use p hat for that, is 0.46 in the problem. So when I took the sample of 200 people, 46% of them said they've received the flu vaccine. Well, I want to come up with a estimate or a confidence interval for the true population proportion P. This is for all people. Let's say all people in the United States who have gotten the flu vaccine. And what they're telling me is this is 0.39 to 0.53. So what that's saying to me is I am 95% confident that the true proportion of all workers who have gotten the flu, who have received the flu vaccine, is between these bounds. I guess we can use percentage here, 39% and 53%. Well, if you read over all of these statements, the only statement that matches our conclusion is statement B. So all the other statements are going to be false. Only statement B says we're 95% confident that the proportion of all coworkers who have received this flu vaccine is between the bounds of the confidence interval 39% to 53%. So answer B is the type of conclusion you come to with a confidence interval. Remember, it's always going to make a statement about the population measurement, the population proportion, or the population mean, because that's the whole reason you construct a confidence interval, is to come up with this estimate for the population proportion or the population mean, which is unknown. All right, let's see, let's do one more here. All right, let's take a look at this one. It says the mayor of a small city is suggesting that the state locate a new prison there. The construction project and resulting jobs will be good for the economy. And it looks like they're going to have a hearing on this. So a total of 183 people show up for the hearing, and 31 are in favor of the project. What can the city council conclude about public support? Well, you know, you have to be careful with this kind of a sample, because it could be that the people that showed up for this meeting had strong opinions on the matter, and other people in the community didn't show up. So I really can't come to any conclusion, because the people that showed up for the meeting were the people that had strong opinions. And maybe they had a strong opinion against the prison. The other problem with this is we're looking for independent responses. Well, when people raise their hands, the responses may not be independent, because if I see the person next to me, you know, let's say the person on my left side raises their hand and the person on my right side raises their hand, I'm more likely to raise my hand. I've been influenced by what I see with other people, raising their hand. So that type of data collection is not really a good way to collect data for this kind of a scenario. All right, folks, hope this is helpful as you're getting started in chapter 10. I'm going to record a separate video for chapter 11. In chapter 11, we do some more numerical calculations for confidence intervals. And for that, I want to show you how to use StatCrunch to automate the calculations. All right.